The wafers are heated in a reaction chamber where a gas flow is maintained. Chemical reactions occur at or near the surface of the wafers, through which the gaseous molecules, called precursors, are transformed into a solid material in the form of a thin film or powder on the surface of the wafers. CVD films may exhibit significant internal stress as a consequence of fairly elevated deposition temperature. This can lead to layer cracking or bending of freestanding structures. There are various categories of chemical vapor deposition, or CVD, characterized by the environment in the reaction chamber. The most popular are atmospheric pressure chemical vapor deposition, called AP-CVD or simply CVD. It is used primarily to grow epitaxial silicon. Low pressure chemical vapor deposition, called LP-CVD, where the reactor chamber is under vacuum, typically at 1 torr. Plasma-enhanced chemical vapor deposition, called PE-CVD, where the energy of the plasma partly replaces the thermal energy, thus allowing CVD deposition at reduced temperature, which is useful, for example, for the deposition of non-refractory metals such as gold or aluminum. Almost all materials can be deposited by CVD techniques: insulators, semiconductors, conductors, superconductors, and magnetic films. The most frequent layers used in micromachining are polysilicon films deposited at 600 degrees C by LP-CVD from silane gas. Low-stress silicon dioxide deposited, for example, by PE-CVD from silane and oxygen between 300 and 500 degrees C. Silicon nitride deposited at 800 degrees by LP-CVD from dichlorosilane and ammonia. In general, AP-CVD produces thin films with a poor step coverage, while LP-CVD offers very good uniformity, step coverage, and quality of the films. PE-CVD provides much more process parameters to control the characteristics of the deposited films, in particular stress. The trend in PE-CVD goes towards the deposition at room temperature with high-density, inductive-coupled plasmas known as ICP.